Testing. Testing on Twitch. Should be live on Twitch. Should be live on YouTube. Go close the door. All right. Let's check it. Is it live? Is it live? Should be here in a second. Testing. Testing. Okay, it's working on YouTube. It's working on Twitch. And then, let's see, it's working on Twitter. How's it going, Josh, John, Amag, Emily, Ed? How's everybody doing? Take a big sip of this coffee here. Excited on this one? Yeah, it should be kind of interesting. I've been changing my workflow. I like kind of cheat nowadays. I basically go and I do a little bit of research. I spend the morning kind of looking up things beforehand. How's it going, Ellie Kate? Perpetual learner. All right, I think the the X has started. So let me go ahead and blow this and then announce the stream. All right, so welcome to another Hoopo stream. The name of the stream today is MemGPT. And MemGPT comes from a paper that kind of has been super popular on social media recently. It's this paper here, MemGPT, Towards LLMs as Operating Systems. This is a paper that came out the 12th of October from UC Berkeley. But I think this paper is kind of more showcasing what viral marketing and naming are doing rather than necessarily introducing a brand new idea, right? Because when I was kind of scrolling and reviewing this paper this morning, I realized I was like, wait a second, this is basically just what other people have been calling RAG. So RAG is Retrieval Augmented Generation, right? And this is a different paper, Self-RAG Learning to Retrieve, Generate, and Critique Through Self-Reflection from 17th October 2023. And what RAG is basically this approach where you're retrieving information and then adding that basically to your prompt such that the language model that you're interacting with will kind of give you more relevant information, right? And what MemGPT is really doing is it's basically the same exact thing, is this idea of a LLM that has some external store of text and then goes and looks for information in that external store of text. It's just that in this paper, the authors decide to really kind of use this analogy of the operating system, but it's really the same thing. So that's one thing to kind of realize, is that this is not necessarily the first paper that introduces this idea. It's just the first paper to have a nice, catchy little title and kind of, I guess, advertise. I don't know how they got a bunch of people interested on this paper and to repost this paper and stuff like that. Okay, so maybe taking another step back, why are people interested in this? And I found this image, and don't necessarily worry about whatever the crap they're trying to advertise here. This is some startup image, probably trying to advertise something. But this is kind of the different ways that people use language models nowadays, right? So most of you probably use it through an API or a chat interface like this, right? Where you directly request a language model. It opens up a new window, a basically brand new context. It maybe populates that with a little bit of a system context, which is probably not even necessarily revealed to you, right? That's kind of like partially hidden from the user, and then you interact, and then once you close out that session, it's over, right? Then there's fine-tuned language models where you take, this is really only possible with open source language models where you can actually fine-tune them and push gradients, but in this case, you're taking a pre-trained language model, something like a Llama 2, then you're collecting a set of data that maybe is specific to your startup or your type of, maybe you're into like Greek literature or something and you have a Greek literature data set. You fine-tune this pre-trained language model on that, and then you interact with it in the same way as these LLM APIs or locally hosted LLMs. But there's this kind of new way. It's not new, right? People have been doing this for a while, but there's a different way that people are trying to interact with these LLMs, which is more akin to something like a lifelong learning, which is kind of terminology from way back in the day, where you want this language model to not be limited to one session and just the limited context window. You want it to basically be able to store previous sessions and then access those previous sessions. Or you want it to be able to store kind of documents and then access those documents later, right? And one way to describe what this is called a vector store. And the reason it's called a vector store is because you're storing the text, right? The raw text that's either previous sessions or specific documents that are relevant. You're storing them with the vector embedding as the kind of index. So that allows you to then go and find the specific documents that you want, right? So in this type of interaction, which is retrieval augmented generation, RAG, R-A-G, you interact with this LLM, but the LLM kind of has a meta process, like kind of like a loop that it's running, where as you're typing shit in, it's going and it's looking at what you're typing and then searching this external database for relevant information and then pulling that up and adding it to the prompt, and not in a way that you would necessarily even see that, right? It might be adding that kind of internally, kind of like a chain of thought that's probably hidden from you as the end user. So why do people want to do this, right? So the reason people want to do this is because until we get 100 million trillion token context length, right, eventually computers will get so much better, so much faster, so much larger memory, bigger compute. Like, you won't need to have these complicated systems, right? Every single piece of text ever written will fit in the context length, and then you can just use that language model as is. But until we get to that point, we're going to need to have this kind of intermediate solution where you want to be able to access external things. Because what people really want, and here I have Andrej Karpathy's Twitter, and he's one of the more famous people at OpenAI, but he's building a kind of Jarvis. So what does that even mean, right? And if you see, he keeps dropping hints about like, oh, look at this, I'm reading about operating systems, and here's me talking about operating systems, the LLM not as a chatbot, but as the kernel process of an operating system, right? I think all these AI companies are really trying to create this kind of lifelong companion, right? An AI service that isn't limited to a single context or a single session, but that can basically be with you the entire time, and not just like 1-2 hour session, but like weeks or months, eventually years, right? So it basically has access to everything you've ever written and everything that everyone else has ever written, and it can kind of pull that in, and it can recall that conversation that you had with it like 2-3 years ago, and so on, right? So we're not literally replacing the operating system. There will still be an operating system that controls all the hardware that this LLM is running on, but the LLM is now kind of the chief operator of your interaction with information. And that is what RAG and then ultimately this MemGPT paper are all about. It's how do you access that information, and how do you kind of retrieve it and store it in increasingly colder and colder storage, such that you have this kind of like seamless experience where it feels like you're talking to something that knows everything and can kind of even reference things that it's seen a long time ago. Okay, so that's a little bit about kind of a little It's like SpongeBob's brain. What does that even mean? I think there's one more image I wanted to show here, right? So I think this is another thing to think about is that why don't I just introduce this? So this is a block diagram of a actual computer, right? So this is like kind of a motherboard, like when you actually open up a computer, like what are all the different parts in there, right? So you might be familiar with kind of the CPU, and that's the central processing unit. What the central processing unit, that's actually kind of like doing all the little actual atomic computations, right? But it doesn't have everything it needs to do those little computations just sitting there waiting for it, right? It has to basically manage the storage and placement of those information it needs for that, right? So it'll have here what's called the RAM, or random access memory. Here is DDR4. There's different types of RAM. There's DDR3, that's like basically generation. So DDR4 is the latest one. And the 2,400 megahertz, that's the speed at which is running, right? Another kind of analogy I like for the CPU is that it's almost like the heart, right? It has like a little heartbeat, and it's like beating really quickly, and that speed kind of determines the speed of all the other things in your computer. So you have this memory here, and then this leads to overclocking, which is whenever people turn up the speed at which these little components operate at. But the CPU is going and it's accessing and putting information in this random access memory here, which is the little actually memory cards that you can upgrade in your computer, right? But then there's colder memory. And by colder, I mean memory that's kind of a little bit slower to get to. So here, for example, let's say here on the SATA. So if you go down, now you go away from the CPU and you get to this SATA port here. The SATA port is what actually connects to your hard drive. And it's not even really a hard drive anymore. Now it's solid state drives. It used to literally be like a little CD that was sitting in your computer, and it's just like reading from this CD and writing to this CD, right? But reading and writing to that little CD that's sitting in your computer is way, way slower than reading and writing to this memory here, the RAM. But the trade-off to that is that the RAM is way, way smaller in terms of the amount of things that it can fit than the HDD, right? The actual little CD. Now it's not a CD, but in kind of my analogy, it's easier to understand it as a CD, right? The CD can store a lot of information, but it's very slow to read and write to that CD, versus the RAM, it can not store a lot of information, but it's very, very fast. So there's this kind of like hierarchy of basically storage where things that are close to the CPU are very fast, but very small. And then things that are further and further away, they can store more things, but they're very slow. And this same kind of high-level concept, people are applying it now to basically language models where, okay, I have the actual context, right? The actual text tokens that are going to be put into the actual attention mechanism for this next token. That's my prompt or my context. But then I have this huge chunk of text that might be previous conversations. And then even colder than that, I might have all the text that has ever been written in human history, right? Like that might be somewhere where you would want to access it too. So this paper and retrieval augmented generation, these are all just different terminologies for this same kind of research field of like, how do I put things and create these hierarchies of storage such that I can retrieve things as needed? Okay. Okay, so Luis expanded on how this is like SpongeBob's brain. Apparently there's an episode in SpongeBob where he has little guys searching through archives. All right, dude. Good to know that SpongeBob is timely, I guess, or timeless. So how is retrieval normally done? So this is a different paper. Sorry, I'm introducing a lot of papers here, but so this paper is In Context Pre-Training Language Modeling Beyond Document Boundaries, 19th of October, 2023. But the reason I pulled this one up is because it has a nice little summary of what retrieval generally encompasses. So to find related documents at scale, we link documents with a pre-training corpus using retrieval models. Okay, this is the important part here. Our retrieval process employs the contriever model. This model maps each document DI to an embedding EDI, right? So you're basically taking your document, which is just a giant blurb of text, or in the MemGPT context, it might be a conversation that you had, right? A previous conversation that you had with this AI. And then you're turning it with the same LLM, right, into an embedding vector, right? So now you're turning all that information into just this vector of numbers that represents that information, taking the mean pooling of the last hidden representation over the token's DI. The cosine similarity is then used to determine the similarity between any two documents. So cosine similarity is basically just you're taking those two vectors and then you're saying how close are these vectors together, right? Are they basically right on top of each other, which means that that embedding and the other embedding are basically representing the same thing, or are they very kind of the angle between them is very huge, which means that they're probably not related, right? And then so here's the actual metric that you're using to determine the similarity between these two embedding vectors. It's just the cosine of the first one and the second one, or basically the angle between those vectors. The retrieval model uses approximate nearest neighbor search, product quantization, blah, 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 FAISS. I think this stands for Fast AI Search. I'm not exactly sure. To conduct efficient pairwise similarity search and so on. So that's how you store and retrieve things quickly, right? You're basically compressing all the information to this embedding, then using that embedding as the index to search for related things. Okay, I think I had some other things here that I wanted to show. Yeah, this was kind of cool. So this is a motherboard diagram for a computer that has two CPUs. So most of you are probably familiar with computers and motherboards that have one CPU. So here you have, normally you have one CPU and then you have maybe 4 sticks of memory, but this one has 2 CPUs, each with 8 sticks of memory. So there's a lot of flexibility here, right? Like these abstractions of like random access memory versus HDD, like those are the result of decades and decades of different little chips being produced and different products being created and then companies being created. So it's not like the architectures and the hierarchies that we employ for computers now are some kind of like perfect, theoretical, optimal way to store and retrieve things for CPUs, right? They're basically the result of this very messy process of evolution and other companies creating other things and then all stacking together. So there's nothing sacred about this kind of CPU, RAM, HDD kind of design pattern. And in the same way, there's nothing sacred about the design pattern that they're going to show you in this MemGPT or the design pattern here or the design pattern here, right? All of these papers, they have their own design patterns, but they're all going to have their negatives and their positives. And to me, this is more a research direction of how do we kind of store things increasingly closer to the actual language model or AI, and then increasingly further and further away with more and more context. Facebook AI Similarity Search, that's what it stands for. It is a library, yeah. It's literally a GitHub repo. People use it pretty much everywhere, this one. It's pretty good because it's also implemented such that it's quite fast. Implemented in C++, optional GPU support, so it's very quick. If you're doing any kind of vector store, you can just literally do it from scratch with this rather than paying some company like PineConeDB or some of these other startups that have offered those solutions. All right, so now that we've kind of motivated a little bit and understood this space, let's actually go into this. So LLMs have revolutionized AI but are constrained by limited context windows, right? So the actual language model itself, right, is this transformer. The transformer is using this self-attention mechanism. That self-attention mechanism has this quadratic computation cost because of the way that it's kind of making every part of the sequence pay attention to every other part of the sequence, which means that the context window is limited. There's a limited amount of text or tokens that you can actually feed into the language model for it to generate the next token, right? So I think eventually that'll be solved, but until then, we have to kind of deal with this scarcity, hindering their utility in tasks like extended conversations and document analysis. And this is kind of what I was trying to motivate beforehand, where what people really want is to make a lifelong AI companion rather than a kind of AI companion that is limited to little sessions, right? Like right now when you go on GPT, it's just these little tiny sessions. Like you're limited to one session and then that's it. And then it kind of erases. You can't reference previous things. And people really want to get to that point where you're basically just interacting with this thing the entire time, and it's just one interaction rather than these little session interactions. To enable using context beyond limited context windows, we propose virtual context management, a technique drawing inspiration from hierarchical memory systems in traditional operating systems that provide the appearance of large memory resources through data movement between fast and slow memory. Right? So this is the fast memory would be the RAM, the random access memory, those little memory sticks that you can put in your computer, and then the slow memory would be the actual like hard drive, right? Which now is a solid state drive. Using this technique, we introduce MemGPT, MemoryGPT, a system that intelligently manages different memory tiers in order to effectively provide extended context within the LLM's limited context window and utilizes interrupts to manage control flow between itself and the user. So another kind of idea that they're introducing here is that there's a faster loop that's running when you're actually interacting with this AI that's determining whether or not to continue to generate tokens for you or to go and add more stuff to the context. And this is analogous to within an actual CPU, right? So even the CPU has subparts within that, right? So it'll have individual processors, but then within that CPU, there's something called the control unit that actually determines when to run things and when to go and fetch things from the registers or the RAM or the HDD and so on, right? And this is a Wikipedia page, instruction set architecture, which is basically the set of supported instructions, data types, and registers that a specific CPU has. So you can actually go and look at this, and much like a GPU has a limited amount of ops or operations, where basically every time you write PyTorch or TensorFlow code, all of that is compiled into one of, I forget how many there is, maybe like something less than 100 different ops, and that's what's actually going to run on your GPU. So the CPU is kind of the same, where there's a limited set of instructions that it can run, and everything that you do on a computer at some point boils down to some specific op or instruction that is run on that CPU, right? So examples of those might be set a register, copy data from a memory location to a different memory location, read and write data from a hardware device, add, subtract, or multiply or divide the values of two registers. So you could see how if you wanted to add two numbers, that would actually consist of first put the number from the memory into this register, put the second number from the memory into this other register, and then add the two numbers in those two registers, and then take that result and put it in this other register, right? So like that's kind of what the CPU is really doing. It's really like grab this thing, put it here, grab this thing, put it here, do this thing with this thing, put that thing there, grab thing here, grab thing there, and the kind of flow or the little piece inside your CPU that's actually deciding what to do that is this control little thing here, the control unit. And that's analogous to what they're talking about here with the they have this interrupt that can manage control flows. Okay. We evaluate our OS-inspired design in two domains where the limited context window of modern LLMs severely handicaps their performance. Document analysis, where MemGPT is able to analyze large documents that far exceed the underlying LLM's context window, and multi-session chat, where MemGPT can create conversational agents that remember, reflect, and evolve dynamically through the long-term interactions with their users. So, kind of what I said before, to me this paper is, like, the best thing about this paper is just they're good at wording, you know? Like, they chose the right words, they're using great analogies, like this here, like, remember, reflect, and evolve dynamically through like this sentence just doesn't really mean anything, right? And technically your operating system right now, the CPU in your computer is doing this. It's remembering, it's reflecting, it's evolving dynamically. Like it's doing that too. It's just that we're not using this flowery language to describe it. So I don't know. I feel like this paper is just a really good name at a good time, and then it has good flowery language that kind of sells it in a good way, versus this paper here, basically the same shit, but like, you know, much more cryptic and less cool sounding name, so it doesn't get the same attention. Okay. Recent years, LLMs and their underlying transformer architecture. cornerstone. Limited fixed length context windows used by LLMs significantly hinder their applicability. LLMs can only support a few dozen back and forth messages. Naively extending the context length incurs a quadratic increase in computational time and memory cost due to the self-attention mechanism. While developing longer models is an active area of research, even if we could overcome the computational challenges of context scaling, which I think we eventually will. So once we eventually do that, then all of this kind of becomes a little pointless. But until then, we got to do these kind of tricks. Given the considerable resources needed to train state-of-the-art LLMs, there is a critical need for alternative techniques. Critical need for alternative techniques. Do you guys have any questions? No. Okay. We study how to provide the illusions of an infinite context while continuing to use fixed context models. Our approach borrows from the idea of virtual memory paging that was developed to enable applications to work on datasets that far exceed the available memory. So virtual memory paging, and here's the Wikipedia page on memory paging. In computer operating systems, memory paging, sometimes also called swapping, is a memory management scheme by which computer stores and retrieves data from a secondary storage for use in main memory. In this scheme, the operating system retrieves data from secondary storage in same-size blocks called pages. So paging is basically going through, the same way that you would page through a book, you can basically page through colder forms of memory and bring it up into the hotter and better and closer and faster forms of memory. So you're seeing how, like, fundamentally all of these things are describing this same fundamental idea of, like, storing and retrieving data in different types of memory, but there's this kind of soup of terminology that has kind of emerged over the decades for describing fundamentally the same process. And in this paper, they basically use the terminology from operating systems to describe that. We leverage the recent progress in function calling abilities of LLM agents. Here they're referring to the Toolformer, which was a paper that basically realized that there's an emergent behavior in large language models where they can call external APIs. They can use tools. That's where the name Toolformer comes from. And one of those tools might literally be external memory or virtual context management, as they're calling it here. We draw inspiration from OS's hierarchical memory management to effectively page in and out information between context windows, analogous to main memory in operating systems. MemGPT manages the control flow between the memory management, the LLM processing module, and the user. This design allows for repeated context modifications during a single task, allowing the agent to more effectively utilize its limited context. All right, and then here we have the figure 1. In MemGPT, a fixed context LLM is augmented with a hierarchical memory system and functions that let it manage its own memory. So these functions are effectively the instruction set, right? So you're basically saying, hey, little LLM, you can do these things here. You can have set a register, which in this case would be create, store something in this external context. That could be one thing. A different instruction could be, hey, go and fetch this thing from this register, which is just putting it there and grabbing it, right? So, like, the analogy of the OS and memory paging and virtual, like, all of those analogies work very, very well, which is why this paper just reads very nicely. The LLM processor takes main context, analogous to OS main memory or RAM, as input and outputs text interpreted by a parser, resulting either in a yield or a function call. MemGPT uses functions to move data between main context and external context, analogous to OS disk memory. And the weird thing is that this main context and external context are also being stored on your computer in either your RAM or your hard disk, right? So, like, the weird thing here is that the external context might literally be stored in the RAM, which is kind of confusing, right? Because here, the main context, the actual stuff probably being stored in your GPU. So the hierarchies, even though they're using the same terminology for both hierarchies, the hierarchies are slightly different in terms of, like, the hierarchy that your LLM is using in this MemGPT abstraction versus like the memory hierarchy in your actual computer that is running the language model. Okay. When the processor generates a function call, it can request control ahead of time to chain together functions. When yielding, the processor is paused until the next external event. Okay. We treat constant context windows as constrained memory resource. To provide a similar illusion, manage where it is placed in its own context, enables the LLM to retrieve relevant historical data. The agent can iteratively modify what is in context for a single task. Okay. Basically, all these paragraphs are kind of just repeating the same thing over and over again. So that's kind of why I'm starting to scroll a little bit here. So you have your main context and your external context. External context refers to information that is held outside of the LLM's fixed context window. This is a nice little table here comparing the context lengths of commonly used models and APIs. So you have Llama 1, Llama 2, open source, 4K, Llama 2, 4K context tokens. And I guess here they chose some arbitrary message size to just give it this to you in message length rather than tokens. But the Claude 2 100K tokens, this is fake news, guys, by the way. Like, it's not actually 100K tokens. I know that whenever they released Claude 2, I think they had a specific example where they copy-pasted the entirety of like some book, and then they changed one of the facts in that book, and then they asked Claude 2 to regurgitate that fact, and it got it right, and then they said, oh, okay, this basically proves that it has a 100K context window, but it's not actually 100K. Most of these LLMs that have a big context, like the Claude one, they're using tricks to kind of compress that, and then those tricks are lossy. So even though it's a 100K token, it's a lossy 100K token. So it's really only kind of getting the flavor of those 100K versus the 4K in the Llama 2, which is much more precise and actually getting the exact thing. Okay. Main context. Because of the importance in pre-prompt in dictating system behavior, it is common for pre-prompt to consume more than 1,000 tokens. So this is the system prompt. I guess here they're calling it the pre-prompt. And this is the prompt that is hidden from you, right? So like whenever you're interacting with ChatGPT, like this is not, what is your system prompt? It's probably not going to tell me, right? But this is not the first thing that it's seeing. There's basically like, what are they saying here? 1,000 tokens before this that basically already put this GPT-4 in a specific type of behavior that OpenAI wants to have, right? So there's already this kind of culture of having a system prompt that is hidden from the user, which I don't really like. I feel like it'd be nicer if they showed me what the system prompt was, but I guess the product companies are going to do what they do. It means the entire context window may be exhausted with only a few dozen back and forth messages. A 1,000 token pre-prompt, roughly the size of the MemGPT pre-prompt, leaves space for about 60 remaining messages. In settings where the user is expected to communicate frequently with the system, it is easy to imagine exceeding the maximum conversation length. Recursive, little typo here, recursive, it should be recursive. Summarization is a simple way to address overflow context windows. However, recursive summarization is inherently lossy, right? So you're losing that information, and eventually leads to large holes in the memory of the system. So rather than having a lossy summary, let's actually explicitly store it. But now if we kind of want to explicitly store it, we're going to have to be able to then search through that explicit store, and now this becomes the retrieval problem. We further divide main context into 3 components: system instructions, conversational context, and working context. I don't like this, you know what I'm saying? Like, this is one of the things that kind of like peeves me about these papers, is that they're all fundamentally talking about the same thing, but like they're creating like just unnecessary abstractions and complexity, right? Where it's like, oh, we're going to call this part the system instructions and this part the conversation. Like, this terminology is irrelevant. You're just like kind of creating these abstractions and then 2 years from now, these abstractions are going to be different, and a different group of people will call these abstractions differently. So like, you're forcing the human being that is reading this paper to have to like create and store these random abstractions that don't really, I don't know. I'm ranting on my soapbox here. Conversational context is read-only with a special eviction policy, and working context is writable by the LLM processor via function calls. Combined, the three parts of the main context cannot exceed the LLM processor's maximum context size, and in practice, we limit the size of the conversational context to a fixed constant determined by the processor's context window. Okay, so some magic hyperparameter there that they choose. And then here's actually the function call that it's using. So this is one of the instructions in the analogy of kind of the instruction set, is it can basically call this external function that appends to this current working context. Prompt engineering with more steps. Yeah, exactly. So that's a better way to describe it. It's kind of like most of these papers are basically just fancy prompt engineering tricks, right? And then they're telling you like, oh, here's the different prompt engineering tricks that I use, but it's like, don't add like unnecessary formal terminology to all the little tricks that you use. At the end of the day, all you're doing in this paper is just storing things externally and then bringing them back. I have to learn 10 new terms. I try not to. That's what's annoying, is that I try not to learn these things because I'm very aware of like my brain is a very limited and lossy storage system, right? So like, try not to store information that is not, try not to even read information that is like not worth storing in your brain, because your brain doesn't know the difference. It'll start storing it, and every time your brain stores something, it's actually secretly pushing something else out that you're not even aware of. So like, yeah, this type of stuff can be fastidious in that way, because you're kind of slowly losing maybe potentially useful information and instead replacing it with a bunch of crap that someone wrote in a paper. Okay. External context refers to out-of-context storage. Analogous to disk memory in OSs. Disk storage, or HDD, right? And it's literally called disk memory because it literally used to be an actual little CD, a disk. MemGPT for multi-sessions. They got recall storage, archival storage. And MemGPT orchestrates data movement between main context and external context via function calls that are generated by the LLM processor. It can decide when to move items between contexts. It can modify its main contexts. So these are all different instructions. Or reflect its evolving understanding. So some kind of like chain of thought of like, hey, what am I doing right now? Is this what I should be doing right now? These instructions comprise of two main components. Okay, more examples. Working context append. Okay. Is there something better here? Welcome back. Experiments. Conversational agents, like virtual companions and personalized assistants, aim to engage users in natural long-term interactions. So this is where they're really all heading, right? This is what everybody really wants. OpenAI, Google, Microsoft, like they all want this lifelong agent that's with you for years and years, and you can basically never leave the window, never leave that session. It's always aware of everything you've ever done. Such an agent must satisfy two key criteria. The agent should maintain conversational coherence, new facts, preferences, and even mentions should align with prior statements. The agent should draw on long-term knowledge about the user, personalized responses. I think the personalization is maybe not as important. To me, it's more about accuracy. So like this paper kind of paints a more important picture where really it's about factual inaccuracies, right? Really, to me, this retrieval is all about, rather than kind of hallucinating a piece of information, actually being able to go look at that exact chunk of text where the information is there in its raw form, and then put that into the context so that you can actually give the actual factual thing, rather than like some lossy version of that is basically then just hallucinated. So I guess that also applies to like previous conversations that you had. Does MemGPT leverage its memory to improve conversation consistency? Can it remember relevant facts, preferences, and events? Does MemGPT produce more engaging dialogue by taking advantage of memory? Does it spontaneously incorporate long-range user information to personalize messages? I don't know why they keep talking about personalization here. Like, is that important at all? Like, does anybody actually care about that? Remember that time we talked about music? What was the artist you mentioned you could get into? So this is the user. Then user is asking about past conversation. This is the self-reflection. So this is kind of like it's talking to itself. Then it's decided to say, okay, I should actually use this function. Now that I've used this function, I'm going to search for music. So notice how here it's searching for music in the recall storage, but how is it actually doing this, right? So the way it's searching is it's probably doing this. It's probably taking the word music, turning that into an embedding, then searching with something like FAISS across all of the previous indexed conversations that it has in this recall storage, finding the one that most agrees with music, or maybe the top 3, and then saying, okay, out of these top 3 that had the highest cosine similarity with what the user talked about here, which of these 3 is the most relevant, and then add that to the prompt and then finally answer the question. So maybe something that I guess they're not talking about here is like the time, right? Like if you're trying to have an AI companion, like all of this takes time, right? It's generating all of these tokens. It's generating these tokens here. It's calling this external function. It then has to wait for that external function to go and search the storage and then come back, and then it has to parse what came back and then add that to the So like from the user perspective, like is it just sitting there waiting for like 20 seconds? Right? There's kind of a trade-off there where the more you retrieve and the better you retrieve it, the more stuff you search in this retrieval process, the better it's going to be. But at some point, a really, really good answer that takes 1 minute is not going to be, from a product perspective, as good as a okay answer that takes 1 second. So there's kind of a fundamental trade-off there that I feel like they're not necessarily talking about here, where they're like, these systems might just take too long. I wonder if it would make sense to train the behavior using a memory. So far, the paper seems very similar, something like AutoGPT. It's a question from Christopher. Yeah, so you could probably, I don't know what I was going to say. I guess it's like AutoGPT in the sense that it has this kind of own internal dialogue with itself, right? It's kind of using this chain of thought internally to determine what functions to call, which is weird and anthropomorphic because we do that, right? We as humans kind of have our own internal dialogue that we like kind of talk to ourselves in order to determine what our next action is. Illustration of deep memory retrieval. So I'm kind of scrolling through this, and it's part of the reason I'm scrolling through this is just because it's like these papers are just generated by GPT at this point. Like these aren't even like written by humans anymore. So like, and really they just kind of say the same thing over and over again. So like at this point when I'm reading papers, I just kind of read the figures. I kind of scroll through, look at the kind of vaguely kind of skim, but we introduce a new deep memory retrieval task based on the MSC dataset designed to test the consistency of a conversational agent. In DMR, the fuck is DMR? We generate the DMR question-answer pairs using a separate LLM. We evaluate the quality of the generated response against the gold response using Rouge L scores. This is a language model benchmark, and an LLM judge. In practice, we noticed that the generated responses were generally more verbose than the gold responses. Performance of MemGPT with the fixed memory baselines. GPT-3, GPT-4, and then MemGPT. Okay, so DMR stands for deep memory retrieval. So kind of exactly what I was saying, where now you have to remember what DMR means, and it's literally just deep memory retrieval. Why not just call it memory retrieval? You don't need the word deep there. You know what I'm saying? That's like a useless adjective there, creating an even more useless 3-letter acronym. The agent is asked with a specific question about a topic discussed in a prior conversation. Methods using the gold persona are marked with that, and then MemGPT significantly outperforms the non-Oracle fixed context baselines. Okay, so obviously MemGPT can access external things, so it's going to have a higher accuracy. This is the precision and recall are metrics for. Am I bringing it up? Yeah, I'm bringing it up. Precision recall. This is like the world's best precision recall figure. That's why I always bring it up anytime precision recall comes up. But precision is how many of the retrieved items are relevant, and recall is how many of the relevant items are retrieved. So in the context of a retrieval language model, right, you have this external memory. Your precision is going to be, okay, you went and you used cosine similarity to get a bunch of things from your external memory. How many of those things that you got are actually useful, right? Did you go and search for the word music and you pulled up like some random conversation about music that had nothing to do with what the user's talking about? That's bad. That's going to hurt your precision score, right? That's going to be red, which means the denominator here is going to be bigger, which means your precision is going to be smaller, right? So precision is going to be smaller is worse, higher is better. Recall, how many of the relevant items are retrieved? So whenever you went and you searched your recall storage for the term music with that embedding vector that represents music and you searched, did you get all of it? Or did you miss the exact conversation that the user's talking about, right? If you went and you found 10 things, and of those 10 things is not even the conversation that the user's talking about is not one of those 10 things, your recall is trash, right? So that's precision and recall in the context of language model and getting previous conversations. So you can see here, the recall doesn't actually seem that high. It's like 0.74. So if you think about this, it's like saying that it only got 70% of the relevant conversations. And out of all the conversations that it got, only 10% of them were useful. I don't know about you guys, that doesn't seem very good. Okay. Conversational opener task. In a conversation opener task, we evaluate an agent's ability to craft engaging messages to the user that draw from knowledge accumulated in prior conversations. To evaluate the engagingness of a conversation opener, what? We compare the generated opener to the gold personas. We also compare the human-generated gold opener because of the quality of the conversation openers. Report the CSIM scores, several variations, MemGPT without working context, recall storage, MemGPT without working context and without recall storage, and MemGPT with both working context and recall storage enabled. So I guess that's what this is. So this is a little ablation study where they say, okay, recall only, working context only. Is the working context just the current conversation? See, this is where the terminology becomes annoying because I don't exactly know what they mean by working context or recall storage. I think recall storage is like the first level, so it's like kind of the RAM, and then the working context is like what's actually inside the language model context. Seems to do a little bit better, but I mean, this is very difficult to interpret as a human. Like, you know what I'm saying? I don't really have a good intuition about what 0.82 versus 0.74 for CSIM scoring means. Here's a more human-readable example here. I grew up studying the LSAT. I want to be an attorney. I used to live in New Mexico. I grew up with horses. I love coffee. I love tea. Gold opener. What date is your LSAT scheduled? MemGPT. Hello there. Just brewing up a fresh pot of tea. How's your coffee? Ready to... Do you guys want this? Like, I don't know if I want this. I don't know if I want, like, this, like, hello, fellow kids, like, cringe AI that's like trying to pretend to be my friend and trying to like pretend that it's brewing pots of tea. Like, do you guys want that? Do you guys want like this corpo language model that just like knows what you want and like pretends to be your friend by like dropping conversation hints? This just sounds creepy, right? I don't know about green checkmark. Like, MemGPT for document analysis. Document analysis also faces challenges due to limited context window. OpenAI's closed GPT. Ooh, look at that zinger right there. Closed AI behind their popular. He's not getting that GPT job or that OpenAI job. He probably will, but you can't be talking shit on OpenAI like that and expect to get an OpenAI job. How else are you gonna get in there? You gotta be nice to them. Anthropic have released closed models that handle up to 100K tokens, but many documents easily surpass that length. So I guess here's an example. The Shining from Stephen King is about 150K words, with roughly equates to 200K tokens. So 100K tokens is not enough, but if you try to think of usually computers scale in the tens, right? Like whenever you're looking at computers scaling from the 60s, 70s, 80s, 90s, 2000s, 2010s, 2020s, right? We're talking orders of magnitude. So right now, the limit might be 100K context, 100K tokens, but maybe by 2030, we're at 10 times that, and then 10 times that. So once you get to 1 billion tokens, it probably seems like more than enough, right? You can probably store the entirety of every conversation you've had with an AI agent in a 1 billion token context. So maybe we're just all sitting around waiting for the GPUs to get bigger, and everything we do until then is basically just a waste of time. Many real document analysis require drawing connections across multiple lengthy documents. It becomes difficult to envision blindly scaling up context as a solution to the fixed context problem. I don't know about that. I can imagine it pretty easily, since they find uneven attention distributions in large context models. The model is more capable of recalling information at the beginning or the end of its context window versus tokens in the middle. So I think part of the innovation that will allow for 1 billion context windows will be much better forms of positional information, right? Like the position encodings that we're using now and position embeddings, I think there's going to be better versions of those that will kind of reduce this effect that they're talking about here. Plus, I also think that part of what's happening here is this attention sync, or I keep bringing this up, but basically in vision transformers, you have certain visual tokens which are getting packed with information that doesn't just represent what is there at that position, but represents kind of a summary of all previous things, right? So there's this emergent behavior where transformers learn to pack information in unrelated tokens. And I think that this paper, Attention Sync, is basically the same thing. Attention Syncs, this one here, right? Where basically they show that the very first token seems to have you can use that as kind of almost like a recurrent neural network, kind of you're storing more information there, and it's kind of a summary of all the previous things. And I think that's analogous to the VIT registers paper, this one, right? Where basically they find that you pack these transformers, emergently pack information into the specific tokens that are kind of the lowest quality, which end up being these background tokens. I think a similar thing is happening with language models, where they're packing information into the beginning of the sentence, the first couple tokens of the sentence. So I think that this uneven attention distribution will get solved. So I don't know if I agree with them on that. I feel like it'll eventually get solved. Document QA and nested KV retrieval task performance. This is the keys and the values. Both tasks, MemGPT's performance is unaffected by increasing context length. Methods such as truncation can extend the effective context length of fixed length models. But such compression methods will lead to performance degradation as necessary compression grows. Compression is particularly bad for key value retrieval since it corrupts the key value pairs. Okay, so here you have levels of nesting, number of documents retrieved. I don't exactly know what they're trying to show here. See if you guys have questions. Maybe it's very computationally advantageous, so we evolve into it. It makes you think if other animals also have some form of tree of thought or dialogue. They for sure do. I think, like, even just looking at my cat, like, it thinks about things. Like, sometimes she'll be looking out one window, and then she'll see, like, a bird or something, and then you can see she gets kind of like, oh, something's happening, and then she goes to the other window across the house to look at the same bird, right? So while she's walking across the house to get to the other window, inside her little brain, she's thinking, I need to get to the other window so that I can see the bird that I was looking at previously, right? So that internal thought process, it's not happening in English, right? A lot of people, they think in their head in language, right? They're almost talking to themselves. Their chain of thought is explicitly in language, but that's not even necessarily how I think. I think my chain of thought is more in these kind of like ideas or like visual, right? It's like in my head, it's like my internal monologue is kind of more visual and kind of like, yeah, visual I think is the best way to describe it. And this is not necessarily unique. I think a lot of other people think in this way too, more visually, but I think that that's actually the way that it's actually a more primitive type of internal chain of thought, if you want to think of it that way, because the chain of thought that's happening inside a cat's head and in a cat brain is probably more visual, right? So, I don't know, some people like to say that visual thinkers are like more advanced and more intelligent than people who think in speech and talk to themselves in their head, but I actually think that visual thinking, which is what I do, is actually more primitive. It's actually what most animals do. Animals are thinking in this kind of like visual chain of thought versus the humans that think in speech and language and their internal narrative is all spoken. I think that's actually more advanced because there's no animal that does that, right? Animals don't really have the concept of language to speak to themselves internally in their head. Or maybe they do, you know, maybe chimpanzees, like whenever they like look at something and they're scared, maybe inside their head they're making the like chimpanzee like screaming sound because they're scared. You know, so like maybe monkeys also have some proto-language internal kind of chain of thought reasoning. Okay. Evaluating MemGPT's ability to analyze documents. We benchmark MemGPT against fixed context baselines on the retriever-reader document QA task. In this task, a question is selected, and the retriever selects relevant Wikipedia documents. Okay, so how good are they going to do on this retriever? The reader model is then fed these documents and asked to provide the documents to answer the question. So accuracy or precision and recall would be good metrics here. In our evaluation, both the fixed and MemGPT use the same retriever, which selects the top K documents according using the FAI-SS efficient similarity search. There it is, dude. Everybody uses this fucking repo. Literally, that Facebook FAI-SS repo is behind every single retrieval and vector storage startup and product that exists. OpenAI's text embedding ADA 002 embedding. So this is OpenAI has, as part of their API, they basically have an API that you give it any arbitrary text and it'll return to you this embedding vector. In MemGPT, the entire document set is loaded into archival storage. The retriever naturally emerges. The top K documents are fetched, similar to the original setup. We use a dump of Wikipedia. Fixed context baselines is capped roughly at the performance of the retriever. MemGPT is effectively able to make multiple calls to the retriever by querying archival storage, allowing it to scale to larger effective context length. Yeah, but doesn't that take more time? You're basically saying our technique is better because it does it multiple times, but doing it multiple times is going to take more time to do it, right? So I think to me it comes back to like one thing that they're kind of conveniently ignoring in this paper is that there's a time cost to more like more chain of thought, more retrieving more times, analyzing what you've retrieved, perhaps retrieving again. Like there's a time cost to that, and like as the end user, you don't want to be sitting there waiting for 10 minutes for your AI assistant to search every single conversation that you've had with it. While MemGPT is theoretically not limited by suboptimal retriever performance, we observe that MemGPT will often stop paging through retriever results before exhausting the retriever database. After sifting through a few pages of irrelevant results, MemGPT will pause the pagination and ask the user to help narrow the query. Okay. So it can basically decide that, hey, I'm not finding what you're telling me here. There's also a trade-off in retrieve document capacity created by MemGPT more complex operation. Assuming MemGPT has the same token budget, a non-trivial portion of MemGPT's token budget will be consumed by system instructions. Yeah, this is huge. So what they're talking about here is that all of these system instructions here, like this internal kind of chain of thought, are consuming the context, right? So like the actual language model, which is predicting the next token based on the previous tokens, these are this is the token, right? So this is something that we've thought about in other previous streams as well, where to me, prompt engineering is almost more about how do I get the same result with less tokens, right? So that applies to chain of thought, right? Where if you're have this internal monologue with yourself, and that internal monologue that the LLM is having with itself has a very wordy and kind of like unnecessarily verbose chain of thought, you're just spending a bunch of your token budget on this kind of unnecessarily verbose internal chain of thought. Like the efficiency of that chain of thought in terms of like actual raw tokens, I think is something that I haven't really seen and seems like a very important problem, right? Like, do you really need the word the, right? I don't know if you need the word the, right? Do you really need the word provided key? Can you just say key is blank? Would that give you the same result? Because if that gives you the same result, I just basically got the same result with 1/3 of the amount of tokens. And like, this is something that I think about all the time when I'm using GPT, for example, for coding, right? So like I might say like, write me a function. Let's do this. For fizz buzz in Python, like that, right? But I could just do, I don't know why I'm talking to DALL-E 3 here, but like I could just do the same thing like this. I could say fizz Python. And there you go. Boom. It's this, I get the same answer, but in 2 tokens. Right? So that to me is like something that is worth looking into, because it doesn't really seem like any of these papers are like really taking that into account of like, how do you reduce the total amount of tokens being used and the verbosity of this internal chain of thought? This trade-off is observed. MemGPT has a lower average accuracy than GPT-4, but can trivially scale to larger numbers of documents. As expected, document truncation reduces accuracy. As documents shrink, the chance of the relevant snippet being omitted grows. Ooh, okay. So now here's a different thing to think about, is that what is the size of the document, right? So when we're storing these documents in our memory that we then reference or search with using our embedding, are we storing each individual sentence? That seems a little bit too much, right? Because if you store each individual sentence indexed with an embedding, now that search process is going to take much longer. But if you store like 10 pages of text with an embedding, that's now too much, right? Because now even if you find the one that is most relevant much quicker because there's less things to search through, now you have to add 10 pages of crap to your context. So there's a trade-off there between how long is each document that you're storing with an embedding in a searchable external memory. So there's so many like interesting design decisions here that I feel like people are not necessarily thinking about. Maybe they are thinking about them. Let's see. We introduce a new task based on synthetic key value retrieval proposal. The goal of this task is to demonstrate how MemGPT can collate information from multiple data sources. The authors generate a synthetic dataset of key value pairs, where each key and value is a 128-bit UUID. So this is just a basically random letters and numbers. Create a version of the KV task where values themselves may be keys, thus requiring the agent to perform a multi-hop lookup. This seems really contrived. What the fuck are they doing here? There's just a really contrived example here. In GPT-4's case, we observe that it often fails to recurse beyond a particular nesting level and simply returns the nested value, unaffected with a number of nesting levels, and is able to perform the nested lookup by accessing the key value pair stored in the main memory repeatedly. MemGPT on the KV task. Okay, so I don't know about that. I don't know about conclusions they're drawing from that. Long context LLMs, search and retrieval, which I really think this paper is just search or retrieval. We should just call this retrieval. Okay, Park et al. Concluding remarks. Let's read the concluding remarks, and then we're going to jump into this one, which is a little bit more formal. So this is basically a paper on the same thing, but it has a little bit more math and a little bit more, I think we can sink our teeth into it a little bit more. I think this MemGPT paper is a little bit fluffy. It's just a lot of text, but really the entire paper is just an analogy of retrieval to operating systems. We introduced MemGPT, a novel LLM system inspired by operating systems to manage the limited context window. By designing a memory hierarchy and control flow analogous to traditional OSs, MemGPT provides the illusion of a larger context resource for LLMs. This OS-inspired approach was evaluated in 2 domains: document analysis and conversational agents. MemGPT could process lengthy text well beyond the context limit by effectively paging relevant context in and out of memory. MemGPT enabled maintaining long-term memory, demonstrates that operating system techniques like hierarchical memory management and interrupts can unlock the potential of LLMs even when constrained by fixed context lengths. Yeah, but another thing to consider here is that in a computer, all of that is local. Right, so going back to here, right, like I think this one. In your computer, the difference between the DDR4 memory and then the stuff here in your HDD, right, it's still all stored locally. So like it's very, even though it's slower from the point of view of the CPU to go to your HDD than it is to go to the DDR4, from the perspective of you, the end user, right, it's basically all happening instantaneously, right? It's all very, very quick because it's just electrical signals going very, very quickly right there sitting on your computer. But what they're talking about here, right, how is that different when hierarchical memory management has to go to an external storage device, right? So you have your LLM, it's running locally on your computer. Is it going to the store of information that's sitting on your computer, or is it going to some S3 bucket that's being hosted somewhere and then getting the information there, right? So like there's so many little design and implementation details there that can basically make or break this, right? Because as soon as you have to go over the internet to go find something and then bring it back, that's so much slower than having to go locally. So like, is all of this sitting inside your local computer? And if all of this is sitting inside your local computer, isn't that going to change all of the hyperparameters, right? Because someone who has 60 gigabytes of RAM is going to have a different kind of optimal set of hyperparameters than someone who has 10 gigabytes of RAM, right? If you're running this on a cell phone, you're not going to have 60 gigabytes of RAM to store previous conversations in for fast retrieval. You're going to have to rely on pinging some external thing that stored all your previous conversations and then bringing that back. So I think the details here and are just a little bit too important, and I think that's going to make this quite complicated to actually implement because it's going to depend a lot on the device that you're using it, what your internet speed is, and so on. How many conversations have you had, right? If you're just starting to have conversations with this lifelong AI companion, you could probably store that locally, but then once you get to a world where you have 10 years worth of conversations, like that's probably not going to work. It's not going to be stored in your computer anymore. Do you have even colder storage? I don't know. MemGPT, integrating different memory tier technologies like databases or caches and further improving control flow and memory management policies. By bridging concepts from OS architectures, MemGPT represents a promising new direction. Yeah, I think this is a little bit trying to pretend like they're the first people to think about this, but to me, I feel like that's incorrect. These retrieval has been around for a while, so you can't just take retrieval, call it MemGPT, and then pretend that you invented it. Let's see, any questions? Will it engage with me? This statement is false. Maybe an LLM can learn to understand the output of something like gzip to get more compressed content. How well does it actually work? Is there an equivalent thing that is a better representation? What are you guys talking about here? OpenAI function API? The OpenAI function API is kind of not that great. So I've tried it out and I feel like it's like too picky and not great. There was a previous coding stream where we tried it out. We wrote our own kind of version of basically a toolformer kind of a function API, and then we used the official OpenAI function API, and I just found the one that we wrote to be simpler and faster and better than OpenAI's function API. I think because OpenAI's function API is probably designed to work for much more complicated APIs where you have hundreds of different functions that you could call, and the difference between two functions might literally be like a single argument or a single quarg or the type of a single quarg, right? Because in a lot of these more complicated APIs, the functions are sometimes overloaded, which means that functions have the same name, but the slightly different arguments result in slightly different behaviors, which means you have to be very picky about the exact function you call. Versus what we found is that when you're using a function API, right, we wanted to call the chat tool. And it said, okay, well, this tool is called chat with, right? And that's not the exact same name. Therefore, I'm going to say that there's not this exact function there. So, I don't know. That's just my opinion on OpenAI's function API. Did they mention how they differ from RAG? They mentioned RAG in the previous work section here, search and retrieval mechanisms, retrieval augmented generation paradigm. It's basically the same thing. At a high level, it's the same exact thing. It's just you're retrieving things from some external memory. Various retrieval mechanisms can easily be swapped or combined as part of disk memory in MemGPT. Interleaving chain of thought, further intrude planning ability. Our work focuses on tackling the problem of equipping agents with long-term memory. Okay, let's go to this paper. So this is self-RAG, learning to retrieve, generate, and critique through self-reflection. And I think the word critique here kind of hints at the fact that they're literally going to train like a critic, so kind of like an actor-critic type situation like you would see in reinforcement learning. LLMs often produce factual inaccuracies. RAG, an ad hoc approach that augments LM with the retrieval of relevant knowledge, decreases such issues. So I would say this definition also applies to MemGPT. However, indiscriminately retrieving and incorporating a fixed number of retrieved passages, regardless of whether retrieval is necessary or passages are relevant, diminishes LM versatility and can lead to unhelpful response generation. We introduce a new framework called Self-Reflective Retrieval Augmented Generation, self-RAG, that enhances a language model's quality and factuality through retrieval and self-reflection. So more chain of thought, self-reflection, internal monologue. Our framework trains an arbitrary LM that adaptively retrieves passages on demands and generates and reflects on retrieved passages using special tokens. So I guess they're fine-tuning in this here. Reflection tokens. So now they're adding special tokens for this. Generating reflection tokens makes the LM controllable during inference phase, enabling it to tailor its behavior to diverse task requirements. Significantly outperforms LLMs on retrieval augmented models on diverse set of tasks. Self-RAG outperforms ChatGPT and retrieval augmented Llama 2 chat. Okay, let's look at the figure 1. Overview of self-RAG. Self-RAG learns to retrieve, critique, and generate text passages. So in standard RAG, you basically get your prompt, you turn that into an embedding, you use that embedding to search over all the different documents that you have in your store. You pull out some K number of those where K is some hyperparameter. Here I guess you have 3, and you literally, in this case, just naively add them to your prompt, and then once you naively add them to your prompt, then you just use the language model to generate the tokens after that, and it'll go ahead and generate that. And I guess what they're saying here is that sometimes that causes issues. So in this paper, they have self-reflective version of that. So how is this different and how is this better? So you have the same prompt, then it's U.S. states got their name from a variety of resources. Retrieve. So similar to kind of what's going on here where it calls functions, right? So if you recall here in this paper, it's calling this search archival storage, right? But search archival storage is multiple tokens, right? If you actually think about this word here, which is search underscore archival underscore storage, how many tokens is this, right? That's, I don't know, maybe like 10 tokens, a little bit less than 10 tokens. Now, in this paper, they're creating new tokens. So they're creating this retrieve token. So now it only takes one token to describe this function. So I think this is kind of clever, right? Where they're basically creating these specialty tokens that are effectively functions, right? Since you keep using these over and over again, you're inside this interaction with the LLM, you're going to constantly have to retrieve things. Just make that retrieval function, rather than calling it this like really long string of letters here and then having to encode that into actual tokens, just make one token that represents that entire thing. So you have a retrieval token, decides whether to retrieve. A relevant token is rel, relevant or irrelevant, provides useful information to solve, is sup, fully supported, partially supported, no support. All of the verification worthy statement and Y is supported by D, and then is use. Y is a useful response. 4 types of reflection token. Each type uses several tokens to represent its output value. The bottom 3 rows are the 3 types of critique tokens, and the bold text indicates the most desirable critique tokens. Okay. So here's the actual algorithm 1, and this is pretty good. I like these. So you have a language model M, you have some retriever R, which is a system that basically encodes the text and goes and finds it. This is your FAISS. And a large-scale passage of collections. This is your set of documents. So you have your input prompt X, preceding generation. I guess that's just previous documents. I don't know what they mean by that. Next output segment YT. M predicts retrieve. So your language model can predict as the next token. It can literally predict this retrieve token. Once it predicts that retrieve token, it basically needs to then predict the next token, and the next token is either going to be yes, no, or continue. If that next token is yes, then it's going to go ahead and retrieve from the set of all documents D. M predicts is relevant for each D in D. So this hyperparameter here of like how many do you retrieve is actually quite important, because if it's 100, it's going to be super slow, but if it's 3, you might have low recall, right, where you might not get the right one. So you're going to basically have a score for all of these. You're going to have the is relevant score, is supported score, and then is useful score. You rank those, and then you pick the best one. Okay. Overview of self-reg at inference. For every X in preceding generation Y, the model decodes a retrieval token to evaluate the utility of retrieval. If the retrieval is not required, the model predicts the next output segment as it does in the standard LM. If retrieval is needed, the model generates a critique token to evaluate the retrieved passage's relevance. The next response segment and a critique token to evaluate if the information in the response segment is supported by the passage. So I like this. I like how the control flow is all in tokens, right? So like the internal monologue of this system here is using tokens to represent specific kind of control flows, right? Like retrieving, is this relevant? Is this useful? Versus here, that's not happening, right? They're not using specialty tokens. They're just using English text, right? User is asking about past conversation, recalling our discussion. I will search my recall memory for the artist name. Like this blurb of text here, which is happening inside the LLM's brain, you're still paying the inference cost of these tokens. So look at this. This is like, what, like 20, 30 tokens compared to what you have here, where now it's just one token. So I really like this idea that they're putting in this paper of just like whatever the common control flows that you end up doing, just make those into specialty tokens so that the total amount of tokens inside like the chain of thought that's going inside the LLM's brain are pretty fast, or there's not a lot of tokens. So maybe this is kind of like an analogy to the thinking visually that I was talking about earlier, right? It's a way of visually thinking with abstract tokens rather than explicitly thinking in English language. Finally, a new critique token evaluates the overall quality of the response. To generate each segment, self-rag processes multiple passages in parallel and uses its own generated reflection tokens to enforce soft constraints or hard control over the generated task output. In Figure 1, the retrieved passages is selected the first time since it does not provide direct evidence. So it even predicts the is useful. So it's constantly kind of like critiquing itself of, is the text that I've generated up until now, YT, given this X, useful? I like that. Enables an arbitrary LM to generate. How are they training this? So if you have custom tokens like this, you're going to have to create your own data set with these custom tokens. So they probably synthetically generated this. Let's see if we can find the exact data collection. Given an input-output pair, we augment the original output using retrieval and critic to create supervised data that precisely mimics the self-rag inference time process. Yeah. So this is the problem. I like the specialty tokens that they're doing here, right, where they're creating these custom tokens that define conceptual kind of control flow things like, hey, I need to go retrieve something. Hey, is this useful? Hey, is this relevant? Versus here, they do it in English. But by doing it in English here, you no longer need, you don't need to fine tune this in any way, right? Because LLMs already understand every single one of these English tokens. But in this case, the negative with this is that you're going to have to basically create your own synthetic data set for this and then fine tune on that. So it's a little bit more complicated in the training process, but it ends up being cheaper in terms of the inference. Versus here, it's less complicated. You don't need any additional training, but at inference time, you're paying for all these verbose English tokens rather than kind of these specialty tokens here. So that's kind of an interesting trade-off there between these two papers. For each segment, YT and Y, which is the generated, we run C to assess whether additional passages, C is their critique, I guess. Critic, so it's kind of like the actor critic. So in what this is kind of terminology from the reinforcement learning world, but in the reinforcement learning world, you usually have there's these frameworks called actor critic frameworks where you basically have the actor is also called the policy, which is what actually takes the actions, right? It's like the little robot that's actually doing the thing. But then you actually then you have a different model, a different neural net that's the critic, and the critic is basically looking at where the robot is and the environment and maybe some steps before, and then it's saying, okay, is this a good action? Did the robot do this little atomic thing well or poorly? So the critic and the actor, those are borrowed terminology here, and they're using critic more here for the LLM that's specifically predicting these relevant, is supported, and is useful tokens. Critique tokens. For each segment, if retrieval is required, the retrieval special token retrieve is added, and R receives the top K passages. For each passage, C further evaluates whether the passage is relevant and predicts is-rel. Critique tokens are appended after the retrieved passage. At the end of the output, Y, C predicts the overall utility token and an augmented output with reflection tokens. We train a generator model M by training on the curated corpus augmented with reflection tokens. Yeah, maybe not, you know? Like, I'm thinking about this more and more, and like I'm trying to predict in the future, like, which of these two techniques would work better. And I feel like part of me wants this technique to work better because I like the efficiency of using these specialty tokens. But then if you kind of come from this, from the Rich Sutton kind of bitter lesson, scale is everything mentality, I feel like this is actually maybe the better approach, is because you don't need to fine tune on these specialty tokens, right? Like, are you going to have like a special data set every time you release a model or use some other open source model that like fine tunes it on these special tokens? I don't know, maybe not. Yeah. Okay. During training, we mask the retrieved text chunks for loss calculation and expand the original vocabulary with a set of reflection tokens. This should be yellow. Connections to prior work. Adaptive retrieval with self-rag dynamically decides when to retrieve text passages by restricting retrieve. Our framework allows a threshold to be set. Yeah, you kind of, and the threshold is going to come from this data set, right? So if whenever you're generating this synthetic data set to add those specialty tokens, like how often are you putting this retrieve token in there, right? Are you putting that retrieve token after every sentence, after every 10 sentences? If you put it after every sentence, then the model's basically going to be retrieving after every sentence. So there's kind of like a implicit probability of generating the yes retrieve token, right? That you're deciding whenever you actually create this synthetic data set that contains these retrieval tokens. At each segment, the retrieval is required based on soft or hard conditions. Generator processes each passage. We conduct segment-level beam search to obtain the top B segment continuations at each time step T, and then return the best sequence. Score of each segment with respect to passage is updated with a critic score S so that the linear weighted sum of the normalized probability of each critique token type. So the S is a score. So the critique is basically just the combination of those three: is rel, is sup, is use. Here you go. So this function, score for a critique, is the sum here for the generated tokens. The sum of all the generated tokens, or the scores, because these are all scores, right? Yeah, I think for all of these, it's basically 1, relevant, irrelevant, so 1, 0, fully supported, partially supported, no, not supported, so I guess 1, 0.50, and then is useful, score from 5 to 1, which then probably gets normalized to 0 to 1. And then you have some weight specific to that critique type, I guess. Critique token type, that's what they're calling it. And here you have the probability of generating that output YT given some previous context X. What's D? Passage D, okay, so some specific thing it retrieves, and then Y less than T, where T is basically the timestamp or where along this sequence you are, so it's all the previous stuff. Okay, so I mean, this is just like kind of unnecessary math to basically say that you're just looking at the scores that you're getting on these critique tokens in order to determine the best output. The weights are hyperparameters that can be adjusted to enable customized behaviors at test time. Okay, so this is kind of cool. So there's 3 different types of critique tokens here. You have is relevant, is supportive, and is useful. So each of those is going to give you a score, but then if you, depending on this WG here, you can determine which one you want more, right? So you can make the WG for is relevant very high, and then is support and is used lower. So you can determine whether you want the retrieved content to be more relevant, more supportive, or more useful. So this is kind of cool. It gives you like a little knob that you can turn at test time to tune the type of retrieval that you're doing, right? Which is something that they don't have here. Right here, it's just kind of like nebulously retrieving stuff based on an embedding, and then just kind of like using internal chain of thought to kind of determine which one kind of makes the most sense given the context, versus here it's a little bit more explicit, and then you can tune it to your liking. Tuning stuff to your liking is sometimes good because you can tune stuff to your liking, but then it's also sometimes bad because the more knobs you add, the more complex and kind of like annoying the user experience is, right? So it's like, you don't necessarily want a product where the user is exposed with like this massive page of like 40 different things that they need to like tune, right? Like ideally you want something that kind of like decides for itself. So whenever we're envisioning like a future AI companion product that is retrieving previous things, like you want the AI itself to kind of determine what the most relevant thing is, right? You don't want it to have to kind of like tune these different weights for these is relevant, is supportive, is useful. I don't know. It's a trade-off, you know? These are all trade-offs. Experiments. We conduct evaluations of our self-RAG on diverse baselines. Short form, long form, tasks, baselines without retrievals, baselines with retrievals, training data and setting. Maybe if they use the same one, this could be useful, but I think they use different benchmarks. Persona, what is the benchmark that they used here? Conversation opener, that's not the one I want. I think they had a more generic benchmark somewhere over here. No, that's it. They don't have any benchmarks that are similar between them, so we can't compare them. That's part of the problem too, is that like these systems, like there isn't really good benchmarks, especially quantitative benchmarks that give you just one final number by which you could evaluate these type of conversational systems that are using retrieval, right? So it's very difficult, nigh impossible to compare this self-RAG system with this MemGPT system. You'd literally have to basically have both of them running locally and then just kind of like ask one, ask the other, and then subjectively say which one you like better, which is actually what happened with text-to-image generation, right? In these text-to-image generation papers, these diffusion model papers that we've read, there was always this kind of two types of evaluation that they could do, right? They could use kind of these quantitative scoring benchmarks, such as the which one am I thinking about? LPIPs, right? Or these things that basically say, okay, this generated image is good, this generated image is bad. And the way that we're going to determine that is some like arbitrary number from this arbitrary metric. But the better way that these diffusion papers would tell you that their diffusion model is good is through these subjective evaluation. Basically, they had people sit down and then look at picture A and then picture B and then say, which one do you like better? I like picture B, right? And I think that you probably need to start doing something similar for these kind of AI assistants that are using retrieval, right? Rather than giving me these fucking scores that I don't know what 42 versus 66 means, right? I don't have any intuition around that. But if you tell me, hey, we got 50 people and we put them in a room that had two computers, one of the computers was running MemGPT and one of the computers was running this self-RAG, and then they had conversations with both of these computers, and then they come out of that room and they say, I prefer this one, right? Like that's pretty useful to me because it says, hey, 75% of people preferred to talk with MemGPT than with this self-RAG. That's good to know versus like here, it's a lot harder for me to really like kind of understand at a human level, like which one of these is actually better. Comparisons against baselines with and without retrieval. Self-RAG demonstrates substantial performance advantage over supervised fine-tuned LLMs in all tasks and even outperforms ChatGPT in PubHealth, PopQA, biography generations, and ASQA. So actually, this is the quick like side tangent. I think this might be one of the first really big applications of these kind of systems, these retrieval systems, is health, right? Like if you're just talking with an LLM and you're just talking to it about like colloquial things like, oh, I'm drinking tea and I'm studying for the LSAT, right? Like, and it looks up your previous conversations to understand that you're more of a tea drinker than a coffee drinker. You know, that's fine, that's cute, but it's not super important that it doesn't hallucinate things and that it gives you the right information. But if you're thinking now about large language models in a kind of health capacity, right? So people are talking about these doctors, AI doctors, LLMs as doctors. those are very, very safety critical applications, right? You don't want to hallucinate text if you're telling someone about like what they should do with their health problems, right? So I think retrieval systems, some of the first like kind of important applications of these are going to be health applications, right? Because you have a huge amount of health papers and health data and textbooks, right? You could just literally take all of the textbooks that they give you in medical school, plus all the most recent papers, put those in one giant external storage, and then have these retrieval systems that you're interacting with. They go and they look for the actual factual information in this like external storage. So like, I think the health and AI doctors are some of the more important and kind of low-hanging fruits, and probably some of the first systems that we'll see that kind of use this kind of retrieval and fancy ways of retrieving and storing. Maybe we even see like a type of system where the external storage is actually regulated, right? Like I could see that. I could see a world where the way to regulate these AI doctors is that they're all just basically doing retrieval, right? Where they're just going to an external database to retrieve relevant information, but that external database is verified by some third-party service that the government regulates, right? So basically, the government says, okay, here's our external database of all the all the medical papers, all the medical textbooks. We've gone through and verified with human doctors that all the information there is correct, and then you, as a AI language model provider, right, you don't have to worry about the factual accuracy and the hallucinations of your language model, because the language model is just going into the government database and finding the relevant stuff, and then just kind of like, really the language model is more just kind of like pushing everything into this conversation, but it doesn't actually have to know exactly what the answer is to your medical question or give you a factual response, and then you as the language model provider are not legally liable for the information that it outputs, because the information that it outputs is basically can be verified in this external government database. So I don't know. Maybe that's interesting to some of you, but I like this idea that I just kind of, I'm saying I came up with it, but obviously I didn't. I bet you other people have already thought about this already, but using retrieval augmented generation as a way to prevent legal liability in healthcare applications that use language models. Coding is a prime use case. I don't use Google and Stack Overflow. I just use Find now. It makes me much more productive. Yeah, coding is another good application for this, right? Because then it just goes and it finds relevant stuff in your code base, brings it back. But I don't know, like, you know, every time I say that, then I also think about, okay, well, in 2030, 10 years from now, we're going to be sitting here in our VR headsets, right? Maybe you guys are talking to an AI version of me, and like we're going to be like, wow, look at how stupid we were in 2023 thinking that we were going to have these external things. It turns out you just literally put all of your code base into one sequence and then just have this giant like trillion parameter context or trillion token context, and it works better than having this like complicated retrieval system. So I don't know. These retrieval systems are great now, but I just feel like 10 years from now, we're not going to be doing this kind of like retrieval. It's just all going to be just one giant blob of information that just self-attentions with the same exact giant blob of information. Our self-reg also outperforms existing reg in many tasks, obtaining the best performance among non-proprietary LM models based on all tasks. Okay, method outperforms other baselines, shows large gains for their non-retrieval baselines. These baselines provide limited solutions for tasks where we cannot simply copy or extract substrings. Baselines with retrieval do not improve performance notably from their non-retrieval counterparts. Most baselines struggle to improve citation accuracy. So these are not, like, I just don't feel like this is a good benchmark, because the problem with this benchmark is that you're just looking at basically things like citation precision and recall. Like it's much like the speed matters, right? Like I could make a RAG model that outperforms all other RAG models by just having a RAG model that literally looks at the top 1,000 hits and like goes through every single one of those hits and then determine, like, you know what I'm saying? Like you can just keep expanding the K parameter, right? The total number of things that it looks, and keep expanding the amount of tokens that you use for this internal chain of thought, and just keep getting higher and higher accuracy. The real trade-off is like, can you do this quickly? Can you find just the best document on the first try, or are you looking at the top 100 documents and then summarizing those and then finding the best out of those and then spending a bunch of internal chain of thought to critique each of those best ones, and then, you know what I'm saying? Like they're kind of pretending like accuracy is the end all be all, but in terms of like an actual user experience, I think the speed is really important too. Take a little sip here. I'm like ranting like a crazy. See if you guys have any questions here. Values of the parameters can be compressed. The amount of knobs can be. Yes. Language. They cannot lie to me on image vision papers. They can lie to you anywhere, dude. They're already lying to you. All text data is lies. You know, like I think from the very beginning of time, like the second that people could write down stuff with text, it was just fucking lies. You know, like I think the very like the book that people would write down at the like constantly was basically the Bible. And what is the Bible if not just like basically this elaborate lie that has been kind of like added on by hundreds of people over thousands of years? You know what I'm saying? Like most of the time when you're reading shit, it's like not actually factually correct. So I'm not expecting the language models to necessarily be factually correct. Like it almost then becomes this kind of argument of like, what is truth? Is there actually truth, or is everything just, it's all lies all the way down? Ablation studies. What do? No critic. So I guess they removed this critic. Hard constraints. Retrieves yes instead of using the adaptive threshold. Is sup. Okay, so they remove some of these critique token types, and then I guess they also training human health analysis, human scale analysis, number of training, num of training, performance. Okay, so it does seem like as you train on a larger synthetic data set that includes these specific tokens, you're going to get better performance. And that's not a good sign for this, because it means that you're going to have to basically train on you're going to have to keep generating a larger and larger and larger synthetic data set that has these specialty tokens in order to get good performance with these specialty tokens. So it's kind of like the curse of the specialty tokens, which is something that we're seeing in different places as well, right? We saw this in the robotics paper. So we read a couple different robotics papers where they were using transformers to output robot motions. And I think in there, they also had this kind of dilemma of like, do we just use English tokens, right? Or do we use kind of custom special tokens that represent things that are robot specific? And it's the same trade-off, right? Where like if you use specialty tokens, then you can have a shorter sequence because you're kind of representing entire abstract concepts as a single token, so you can have faster, right? But then the problem is now you have to train, you have to create some kind of synthetic data set that has those specialty tokens. So, you know, the curse of the specialty tokens. Compare the performance. Show that the model's performance trained on difference. Increasing data set size often shows upwards trajectories, and significance are significantly larger. Further expanding the training data of self-RAG may lead to further improvements. Turtles all the way down. All right, conclusion. This work introduces self-RAG, a new framework to enhance the quality and factuality of LLMs through retrieval on demand and self-reflection. Self-RAG trains a language model to retrieve, generate, and critique text passages and its own generation by predicting the next tokens from its original vocabulary, as well as newly added special tokens called reflection tokens. Self-RAG further enables the tailoring of language model behaviors at test time by leveraging reflection tokens. Our holistic evaluations on 6 tasks using multiple metrics demonstrated that self-RAG significantly outperforms LLMs with more parameters or with conventional retrieval augmented generation approaches. Okay. Pretty much it, guys. Let's go to the top here. If you guys have any questions, ask them now. I'm going to take this last sip of coffee, and then we'll summarize these 2 papers and what we think of retrieval and where this is all going and whether or not we're gonna survive. Which LLM did they use? I think they used Llama. So in this paper, they need to use a language model that they can fine-tune, so that my guess would be Llama 2. Let's see if we can actually find it. Llama. We use the same one as the generator LM, so they use Llama 2 7B. Yeah, this one does not need Llama. So because they don't need this one, because they don't have the specialty tokens, they don't need to fine-tune it, and because they don't need to fine-tune it, they can just do everything in text, which means that they can just use GPT. So this one uses GPT-4. So MemGPT is GPT-4, and then this one uses Llama. Was the fine-tune worth it? We'll never fucking know. You know, like, they don't evaluate on the same benchmarks, and the benchmarks that they evaluate on are kind of like these quantitative benchmarks that are difficult to interpret, and they're comparing against old crusty things that no one uses anymore. So, you know, ideally we would want to get 50 random people and get them in front of both of these things and then tell us which one they like more, and then that would, I think, be the best way to determine whether or not it was worth it. But we're basically never going to get that test. Okay, let's go to the top here. Let's summarize what we did today. So today, this stream was called MemGPT, but really this stream was more about the concept of retrieval and language models using external memory stores to improve their generation. You can find all the links that I opened up here on this GitHub page, Stream Docs. You can find the links and thumbnails for any episodes. So MemGPT is short for Memory GPT, which is a paper from Berkeley that basically takes GPT-4 and has a way of storing previous conversations and any kind of text blurb in an external memory that it can find and index and access. So in this paper, they really kind of like narrow in on this analogy of a computer, right? Inside a computer, you have this kind of basic components of the CPU, the central processing unit, and then you have the memory, right, which are these sticks, and that's called the random access memory, and then you have the hard disk, or the HDD, or the cold storage, or the solid state disk. All of those words are basically the same thing, but the high level idea is that the thing that is actually doing the instructions, the operations, can, as part of those sets of instructions, decide to go find information that is stored elsewhere, right? Copy data from some memory location to a memory location somewhere else, right? So moving information around so that it can better do some specific operation. And in this MemGPT paper, they basically take this analogy and then design this effectively retrieval augmented generation, except they for some reason really avoid using the word retrieval here, even though this is literally just retrieval augmented generation, right? But they kind of really kind of overuse this analogy of the operating system to basically do a fancy retrieval augmented generation where you're basically storing parts of previous conversations into this external stuff, and then you can go and search and find it and bring it back. The way that they're doing it is they're doing it through a kind of a function API. So basically the the language model is in its own internal chain of thought, right? Its own internal little monologue. It's saying, okay, I should go and find something related to this information. Let me go and find that information. Okay, I found this information. Is it relevant? Is it not relevant? It is relevant. Okay, then I'm going to paste it into the context, and then I'm going to generate as if it was in that context. And all of that internal kind of chain of thought is all happening away from the user. So from the perspective of the user, right? So here's kind of like a diagram showing you from the perspective of the user, it asked a question and then it gets Taylor Swift, right? Like that's the answer, right? And all this crap here happened all internally. So the second paper that we were looking at today is called Self-RAG, Learning to Retrieve, Generate, and Critique Through Self-Reflection. And this is also a retrieval augmented generation paper where it's all about the language model going and being able to search an external memory bank of basically documents and text that it can then kind of bring in to the context of this specific session to give you a better answer. And the main kind of thing that they do in this paper is they create these specialty tokens. So they create these special tokens, which they call critique tokens. And there's basically a couple of them. Here you have a token that represents the concept of retrieving, a token that represents whether something is relevant, whether something is supported, or whether something is useful. And then basically, when you're interacting with this LLM, and in this case they use the Llama 2, it's actually going and it's actually predicting a token. So every so often, it'll predict the next token as a retrieve token. And then when it predicts that retrieve token, it'll then answer its own question and say, should I retrieve here? And then based on the tokens that come beforehand, which are your question, it'll say, okay, retrieval is important here. Go and then retrieve these passages and then tell me whether each of these things that I retrieved is relevant, is supported, is useful, so on, right? And it works nicely, but the problem is that now that you've introduced these specialty tokens, you need to fine-tune your language model on examples that include these specialty tokens, right? So if you just take a Llama 2 out of the box, the Llama 2 out of the box is never going to use these specialty tokens because it's been trained on data that doesn't use these specialty tokens. So the benefit of the specialty tokens is that you don't have to be using English, right? You can, instead of having this like 2-sentence like blurb here inside your internal chain of thought, which is costing you tokens, you can just use a single token, this retrieve token. So it's faster, but the negative is that now you have to basically fine tune on some kind of synthetically generated data set that has all these specialty tokens in it. And the double bad news is that it turns out that the bigger your synthetic data set is for these specialty tokens, the better you are. So you're basically effectively coming to the realization that in order to create a RAG model, you're going to have to basically have a huge synthetic data set of these specialty tokens in that data set, which probably isn't great because the bigger your data set, the more it's going to cost to fine tune. And the more it costs to fine tune, the more money you're going to require. And at some point, the amount of money it takes to do that is more than the amount of money that it takes to pay for the extra inference cost of just having it in plain English. So there's all these little trade-offs that we kind of talked about today about, because to me, okay, so kind of pulling back from both of these papers, to me, the fundamental thing that you're trying to solve here is trying to have a factual conversation with an AI agent, an AI that can go and find information for you and then puts that information inside the conversation in a quick way and in a good way, right? So there's a fundamental trade-off between how fast is it and how good is it, right? If you have to spend a bunch of tokens going and finding things and then going to some S3 bucket to find something and bring it back and then have an entire chain of thought to like evaluate each of those, it's going to take very long, right? So maybe that user experience is not going to be very smooth because, like, sure, the AI is like, is telling you things that are relevant and useful, but like it takes very long in between questions. On the other hand, this one, it's going to be more annoying to train, but it's probably going to be a little bit faster because these specialty tokens are shorter, but then both of them have the same hyperparameter of just how many things are you retrieving when you retrieve. So there's a lot of like design decisions in these systems that it doesn't really seem like these papers even try to really answer them, right? They just kind of say, hey, we kind of said we're going to pick the best 3 and then we're just going to go from that, right? Like it seems like those design decisions are going to make or break everything. And to me, I feel like one thing I came out of this wanting is like a subjective, qualitative evaluation of people using these systems for some kind of real world task. And I think what I liked in this paper is they mentioned medical, and I think medical is probably the very first application of this, because it's like the perfect combination of like, hey, I have all this factual text data, which is like medical textbooks, and there's this really important kind of safety pressure that is forcing me to be very factual with the information that I'm giving you in this health context. So I feel like health LLMs are like the perfect tip of the spear for evaluating these type of retrieval augmented language models. So yeah, I don't know. I think that's where we're going to see these first. And to me, I think this is actually a great way to make things, to remove that kind of legal issue that we have now, where like, are you as the language model provider responsible for the factuality of the outputs of that language model? I think right now it's yes, right? If you have a large language model and it tells your user that it needs to like rub garlic on its eyes in order to cure its cancer, like, and then the person dies of cancer, like they might be able to sue you and say, hey, like your language model was telling my friend bullshit, and then they followed that bullshit. But if you, as the large language model provider, can say, hey, my language model doesn't know anything. All it does is it goes into this medical corpus here, which the government has set up, and then it pulls out the stuff from that. So if you have any problems with the advice that it gives you, just go and sue the people who provide the medical textbook stuff. I think this is actually a good solution to that. But the other kind of low-hanging fruit that people are going to do with these kind of systems is what Karpathy is working on, right? So Karpathy at OpenAI, he's kind of famously working on this Jarvis, and what that means is basically going to be more like the LLM is aware of previous conversations, so it's less about the factuality of what it's telling you, and it's more about kind of having an LLM that kind of understands all the previous times you've talked about it, and you can say, hey, like a year ago, I remember reading something, and it's like, oh yeah, here, I have that conversation, let me pull it up, and now I can talk to you. So the other kind of side of the coin with these retrieval systems is the people who are interested in this kind of like lifelong learning, like lifelong buddy, basically kind of understands you deeply because it has a huge memory bank of all the stuff that it's done with you, and it can go and then pull from that. So those are kind of two kind of applications of these systems that I can see emerging quite quickly, probably within the next year. But yeah, that's it, guys. If they are dead, they can't sue, I guess. All right. So that's going to be it, guys. 56. Thanks for this. Hope this was useful. And yeah, drop by the Discord if you guys want. You can recommend papers and chat with a bunch of cool people. Answer and ask questions. Sometimes I give answers. Thanks, Josh. Thanks, John. Thanks, Emily, Amag, Ed, Tafuk, Alik, Perpetual, Luis, Christoph, Cellophane, Luis again, Cellophane again, Random Bot 44. Everybody, thanks you for the questions. Thank you for the conversation. Hope this was useful, and see you guys next week.